Well, shoot, I couldn't fit all my blah blah in my last video, so this is the dramatic conclusion of entropy estimates and such, or my first thermodynamics video, which is the following has a negative entropy change. That is to say, what is that to say? That is to say, the system becoming less entropic, less messy, less disorganized. So when water freezes, it goes from a liquid to a solid. And what happens to the entropy of the particles going from a liquid to a solid? Yeah, that's it. That decreases. Hopefully all the rest of these have an increase in entropy. Oh, wait a minute. Which is the following? Okay, so multiple answers. So how about this one? Water freezes from a liquid to a solid. Or an alcohol vapor condenses into a liquid. That's also a negative entropy change. A gas at 555 going to the same gas at 400 Kelvin. That also is a negative entropy change. Cooling in that sense, anything cooling down. Or going from a gas to a solid, that would be a negative entropy change. So you know what, it's all those. And you know what, under not all circumstances would these go by themselves, because nature does not really prefer, in most cases, to become more organized or less disorganized. The following, which system shows a decrease in entropy? Oh, same question, different possibilities. Decreasing entropy, not that common. Excuse me. Liquid to a gas? No, that's increasing entropy. Alcohol liquid evaporating to a gas. Solid salt dissolving in water to become aqueous? That's an increase in entropy. That's not it. Gas. This has, oh my goodness, excuse me, 2 moles of gas on the right, 2 moles of gas on the left, 1, 2. So I'm looking at this one as not changing entropy much at all. 2 moles of gas here, 2 moles of gas here. I suppose since this is more segregated and organized into nitrogen gas and oxygen gas, this might be increasing in entropy a little bit, but not based on the moles of gas. Here we have 2 moles of gas. Here we have 1 mole of gas. So this one's right here. This is decreasing the entropy, going from 2 moles of gas to 1 mole of gas. Yeah, that's what I just said. Okay, let's see. Second law again. Whenever the entropy of a system changes, that means the surroundings likely has a corresponding entropy change as well. For reversible processes, the change in entropy of the universe is 0. For most, you can't go backwards all by themselves processes. The entropy change is positive. The universe likes to increase the messiness. Oh yeah, this is called the second law of thermodynamics. Let's see, I like to say it's when your mom asks you or used to ask you why your room was such a mess, you just say it's the second law of thermodynamics. I can't help it. Nature just wants to become more disorganized, more messy, more entropic, they say. Yeah. So here's the universe, here's the system, here's the surroundings. The system might be like your beaker or your container, and the surroundings is the room around, and all to consider together, we're looking at the universe hopefully increasing the entropy. This is sort of one reason why heat always flows from hot to cold. It melts the ice. The heat energy, enthalpy, goes from making ice at 0 to liquid water at 0, and the only difference is the entropy of the liquid water is greater. Here's a lot of blah blah. What's up with that? Let's read the bottom line. Entropy increase must come from heat released by the system. The process must be exothermic. If a process is to be spontaneous, there's one exception to that. Let's look at a graph, a comparison. So here's my entropy of the universe. The entropy of the universe should be increasing for a spontaneous change. If my system gets less entropic, so more organized, then my surroundings must get even more disorganized. So this one plus this one has to equal a positive number. This bar is a little bit higher than this bar is down negative. So I guess this represents a spontaneous process. Yeah, that's what I just said here. This is spontaneous. But sometimes if things change, then this is approximately the same as this, but my surroundings did not increase in entropy as much. So this one plus this one comes out to a negative answer. I could assign numbers to these. And a negative change in entropy of the universe means it doesn't really favor that happening all by itself. There's a way to calculate the entropy change of the surroundings based on the enthalpy change in the temperature that happens in the system. And that's it. That's a simple equation. I think I have a slide down here. I'm going to have to come back to this one and look at it. Often if the system's heat changes, the negative of the surroundings heat change. One gives off, one takes in. That's why the negative there. Let's try this before I try that equation. Predict the conditions under which the following would happen. I have sulfur hexafluoride gas going to a liquid, so a gas condenses to a liquid. I don't know. That's not very favorable. What condition would you have to have in place in order for your gas to go into a liquid? Wouldn't it have to be darn cold? Yeah, I think it would have to be very cold. So low temperatures slow these gaseous particles down slow enough that perhaps they can stick because of interparticle forces into a liquid. Let's go with that one. So there are some environmental conditions that favor entropy change, or in one way or another, or not. Let's see. So I burn 1 mole of propane in oxygen, carbon dioxide, and water. They give me a heat number for that. Enthalpy change. Exothermic, it's negative, right? Negative 2044 kilojoules. Well, just divide that. Oh, there's a negative in front of the equation too. So negative of the negative makes a positive, and the Kelvin temperature is 298. So this divided by 298 gives me a positive entropy change of 6 or 7 kilojoules, which for entropy change, kilojoule, that's fairly large. That's quite a bit of, so the surroundings get a lot more messy, and that's because of the release of this heat. That's worked out for you in a different way if you like to see it. Reaction below. How much time do I have? Oh yeah, I'm at 7.5 minutes. I got some time. I'm almost done though. 2 more. Last slide. Yay, last slide. So endothermic, 66 kilojoules. Determine the delta S of the surroundings. Let's see, I didn't write this out. What would I do? Oh yeah, the delta S of the surroundings equals the negative delta H of the system divided by the Kelvin temperature. So how about if I just take the negative of this, which is negative 66.4, divided by 298 Kelvin, and that should give me my entropy change. Oh, it's down there. It's on the PDF. Do you care to see it? Also, you can look it up. You can look it up on the PDF. Let's see. The sign of delta H of the system. Oh yeah. I'm sorry. Delta S of the system. Well, delta S of the surroundings is negative 66.4 divided by 298. So it'll come out negative. So if my system, if my surroundings has a negative entropy change, then my system will have a positive entropy change because one's the opposite of the other. The system is giving the surroundings the entropy. Well, in this case, it's actually taking in entropy. Is that true? Yeah, that's true. And is this process spontaneous? So if I'm endothermic and my entropy decreases because it's negative, no, wait a second. The system, oh, my bad. So as I was saying, let's get this right. I should have written this out. It's written for you down below here. Take a look at it. If my surroundings have a negative 66.4 divided by 298 negative number of joules of entropy change, my system goes from 2 moles of gas, 3 moles of gas to 2 moles of gas. So from 3 to 2, that's also a negative entropy change, creating fewer moles of gas. So it's just, both are negative. and that's decreasing in entropy. And so spontaneous, I don't think so. All right, shut up. Thanks, guys. See you in class.